Hello everyone, this is the part 2 video for MA162 exam 1 fall 2021 where I will go through questions 7 through 12. For number 7, we have this fancy graph here of a isosceles triangle and we are given the y component of like how this base area, this base length is. And we are to find the volume that it creates when you go through this entire sort of like a semicircle, right? So first, the idea of this, right? The isosceles triangle, the base and the height is the same, right? The hint, right? So base equal to height equal to whatever the y value is at that x, which is cosine square root of cosine x, and then think about how the volume is created, right? It's sort of like really small individual slabs of isosceles triangle, right? Each one of them, isosceles triangle slabs are, so we do the area times like the height or the thickness rather, right? So this is just dx, right? It's so thin that we use calculus, right? It's just a very small sectional area length of that x, and the area here is just area of a triangle, right? 1/2 base times height, which is 1/2 square root of cosine x times square root of cosine x, which is just cosine x over 2. So that's volume of a single the triangle slab, right? But then when we put it all together, we can just use integral to get the whole volume here. So integral from negative pi over 2 to pi over 2 times cosine x over 2 times dx, right? That's just the volume of 1, and I'm integrating over all of them. It should be a pretty simple integration, right? The integral of x, cosine x is just sine x, right? And we're evaluating over from negative pi over 2 to pi over 2, right? So sine pi over 2 is 1, so we have 1/2 minus negative pi sine pi over 2, or sine of pi, negative pi over 2 is -1, so negative 1/2. In total, we'll get 1 as our final volume, which I think was option B. For number 8, we're again given a few functions, and it's revolved around a line y equal to 1, which would be a horizontal line. So let's graph this. All right, let's graph this. All right, so we have, let's say, y equal to x square root of x, something like that. We have the x-axis, x equal to 1, be a vertical line which meets the square root line at 1. And then all of this is revolved about the line y equal to 1. So all of these meet right there. Right, it would be this area. Right, there's two ways, right? There's disk washer or the cylindrical shells method, right? For disk and washers is generally like pi r squared ish. So r being the radius away from the revolving axis, right? Dx or dy, and then the cylindrical cells is 2 pi RH, right? Whatever you're doing the derivative of. But looking at all the answer choices, right? It's not like completely written like and solved. So I would say that all of these are actually just um, cylindrical shells, since all of them has the 2 pi in front, right? Notice how cylindrical shells has a 2 point in front, so that's probably the preferred method, although it's not specifically stated in the question. I would just not use the disk washer method, rather use the cylindrical shells on this question, since that's what the answer choices are given us. With that being said, let's think about the cylindrical shells. Let's use green. So once it's revolved around, it will look something like this, right? So where the cylindrical shells are coming in then is like so. So if I have this thing, that would be a cylinder, right? And then a bigger one. So then we can kind of get a sense that um, this would be, your integration would be in the y-axis, right? Because the radius of your cylindrical shells are getting bigger with the y-axis, right? The radius here might be like 0.5 and then 0.6, 0.7, etc. So our general direction would be dy, whereas the radius would be the y value, right, away from the y equal to y equal to 1. So since our function is here, right, so um, the radius would be 1 minus y, right? So if we are here, then it's 1 minus y being 0.5 maybe, or 0.4, then 1 minus y, the radius will be 0.6. So we get r is that, and then h will be the height of the cylindrical shell, right? That would be, right, this part, which is bounded by the x equal to 1 line and the parabola, I guess, if you're looking in the y direction. So you need to rewrite this equation to x equal to y squared. So then now the height of the cylindrical shells are 1 minus y squared, right? So we have 1 here, and then the y squared parabola here. So then you can write the integral just being 2 pi, where we use cylindrical shells, times 1 minus y times 1 minus y squared. All of that is taken over dy. So that'll be option A. But yeah, this question is really about can you see this in the dy perspective, right? Can you see how the height is, right? The x equal to 1 line minus the x equal to y squared line, right? For question 9, instead of giving us the function asking for the arc length, we're giving the arc length urge to find the function. So for both those problems, we generally want to know the arc length formula. So from A to B, it would be 1 plus dy dx squared dx, right? That's the general arc length formula. So then we can sort of go backwards from here, right? We see the square root is here, the integration and the dx is all here, right? We just take all that out, so we can say something like 1 plus dy dx squared equal to 9x to the 4th plus 6x squared plus 2, right? And then we have generally dx dy squared equal to 9x to the 4th plus 6x squared plus 1. And you would notice, if you have a sharp eye, that this is actually a perfect square, right? If you can't see that right here, 9x to the second, 9x to the 4th would be a perfect square, and right, it would be 3x squared, and plus 1. If you write this out, it will actually just be that. So that's a perfect square. We can write it like that. So then we can just square root both sides and get rid of the square. We have dy dx equal to 3x squared plus 1. Now we can just integrate both sides, right? And then for this part, the integration and the derivative cancels out. Right, we want to integrate over dx, right? Dx cancels out, the derivative and that cancels out. So we have y would just be x cubed plus just x plus a c, right? But we just find a function. So this function would do. So for number 10, we're given an equation and asked if this equation is rotated around the x-axis, what the surface area is, right? So first of all, let's write down the surface area equation, which is the integral of from, let's say, a to b. In this case, it will be 0 and 3 to the 4th root, and 2 pi y. In this case, would be x to the 3rd divided by 3 times the arc length, right? So arc length, which in this case, right, arc length is like the arc length equation. That's how I usually remember it. So 1 plus dy dx squared, and all that is dx. So it's not necessarily the arc length because the arc length has some integrals in it too. But generally, that's the equation we're going to use. Let's use blue here. So the surface area we're calculating then are, right, the bounds 0 to 3 to the 4th root, 2 pi times x to the 3rd divided by 3 times square root of 1 plus dy dx. So that would just be x squared squared. Right, just take the derivative of that, all that dx. So simplify a little. Actually, let me just bring the 2 pi out. I'm not going to write the bounds because it didn't change, right? So we can also take the 3 out. X squared times root 1 plus x to the 4th dx. Right, so here we're going to integrate this, which can be somewhat intimidating to see the x to the 4th, right? But the trick here is to a u substitution. So let's write it in purple. U, if I say u equal to 1 plus x to the 4th, right, then du Simply, I take the derivative of that is 4 x to the third dx, right? Take derivative on both sides, so that x becomes, there's a dx and a du on the other side. So notice in the equation, I have the x to the third and the dx. So I'll just make that on one side. So divide the 4 over, right? So now I can replace, or I can replace these two with du over 4, and I can replace inside the square root the 1 plus x to the 4th with u. Outside constants don't change. I'm not going to worry about the bounds of the integration for now. I will u sub x back in and then use the original bounds of integration. So here we have, right, square root of u, this part, du over 4. Right. I can also just bring the over 4 part outside. So we have, so that's 1/6 pi over 6, root u du. Now this is a pretty simple, just chain rule. Keeping the constants outside, we can just integrate that. So that would be u to the 3 over 2. And then remember to chain rule. I'm not going to worry about the bounds of integration for now, since I'm going to plug x back in for u. And we don't need plus c because we have, it is a bounded integration. So cancel out the constants, and I'll plug in x back for u. So here, that would be pi over 9. And plug x back in for u. So 1 plus 4 x to 4 to the 3 over 2 power. And all that is integrated, or rather evaluated, at the original bounds, 0 and 3 to the 4th root. So now all the u sub is done. We just plug the bounds in. Pi over 9, have 1 plus, so the 4th root and the 4th power cancels out. 1 plus 3 and minus 1 plus 0, pi over 9. So that's 4. Root 4 is 2. 2 to the third is 8. Minus 1 to any power is 1. So our final answer would be 7 pi over 9, which would be C. For question 11, we're given 4 equations, and we're to find the volume generated by rotating around the x-axis. So first, let's draw this. Right, so x plus 2 equal to y. Just a straight line, and then same slope, x equal to y. Right, and then there is the vertical line, x equal to 0, and x equal to 2. Right, so our limit of integration, right, if we're doing dx, will be 0 to 2. And since that's where, right, it's really just this region here, flipped over, rotating around. So this is just a washer, right? So we have the general equation of pi r1 squared minus pi r2 squared, right? And then we can see that the x plus 2 line is above the x line. So we just do x plus 2 squared minus x squared dx. All this would be 0 to 2. Let's say the volume equal to, right, this is x squared plus 4x plus 4 minus x squared. X squares cancel out. We have 4x plus 4. Right, we can take the pi and the 4's out. Alright, let's write it over here. So we have 4 pi x plus 1. Integrate to 2 plus x, that over 0 to 2. Right, 2 pi times, that would be 4 over 2, so 2 plus 2 minus 0 minus 0. Total, we get 16 pi. For question 12, we have a integral application with the spring force. So generally, right, the force generated by a spring is k delta x, right? K being the spring constant times the distance away from the equilibrium position. So first, we need to calculate this k since it's not given. Right, we have a force at a distance from the equilibrium. So we have 40 Newton is the spring constant times 0.1 meters. All right, spring constant, then it's just 400 Newton per meter. So now, all right, we can sort of get work, right? Work is the integral of force over distance, right? dr being just a distance, whatever, dx, dy, or dz, whatever your distance is over, what direction. So here we just plugged in the f, right? K delta x, or make it simpler, just kx dx, right? And then k is 400 here. So we just solve the integral. X squared evaluated at, let's see, 0.1 to 0.2. As it's from 0.1 meters from the equilibrium to a 0.2 meters from the equilibrium. So plug in 400 here, we get 200 x squared. Right, the work would be 0.2 squared, 0.04 times 200 is 8, minus 0.01 times 200, which is 2, which is 6 Newton meter. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.